Welcome back. We will now continue with part 2 of basic ultrasound physics. Let's look at the properties of ultrasound. Ultrasound is sound waves with a frequency above 20,000 Hz. This is above the normal hearing capabilities of humans. The basic properties of ultrasound waves are the same as audible sound. The frequencies used for medical diagnostic imaging are in the range of between 1 and 20 MHz. The diagram shows the range of frequencies of sound waves, and shows where ultrasound is relative to audible sound and other higher frequencies of sound waves. Let's now look at the process and underlying principles of how ultrasound waves are generated. Medical ultrasound waves are generated by piezoelectric crystals. These are transducers that convert one form of energy to another and vice versa. Piezoelectric crystals used for ultrasound are lead zirconate. Application of electrical energy to these crystals cause them to vibrate at a defined frequency based on the properties of the crystals. The crystals will also convert mechanical sound vibration into electrical energy, thus allowing for returning sound waves from reflected structures to be interpreted and an image generated. Piezoelectric crystals are examples of transducers. Transducers have the capability of converting one form of energy to another. For ultrasound, the energy converted is from electrical to mechanical and vice versa. The frequency of sound waves produced is dependent on the thickness of the crystals. Thinner crystals will produce ultrasound waves of higher frequency, whilst crystals that are thicker will produce ultrasound waves of lower frequency. The ultrasound transducer acts both as emitter and receiver of ultrasound waves. After emitting ultrasound waves, there is a pause, where the transducer waits for reflected ultrasound waves to return to the transducer. The reflected waves cause a mechanical deformation of the crystals, which is converted to electrical energy. To summarize, the processes involved in ultrasound generation to image formation start with the piezoelectric crystal first. A high-frequency electrical current is applied to the crystals, causing them to vibrate with high frequency. The crystals vibrating at high frequency produce ultrasound waves, which are then directed towards the tissues to be imaged. Returning ultrasound waves that are reflected by the tissues are picked up by the crystals. The crystals convert the returning echoes to electrical energy, which is then processed and interpreted to form an image on the display monitor. The diagram shows the basic principles of how ultrasound can be used to generate images of tissues. As the machine assumes a constant speed of ultrasound through tissues, the time taken for the transmitted waves to return to the transducer allows for the depth of the tissue being imaged to be determined. This allows for ultrasound images to be generated. Let's next look at the interaction of ultrasound with tissues. This is important for image formation and also explains why artifacts are produced. Ultrasound waves undergo four main types of interactions with tissues. These interactions are described as absorption, reflection, scattering, and refraction. These are shown in the diagram here. The above interactions are responsible for attenuation of the ultrasound beam as it travels through tissues. These interactions between the ultrasound beam and the tissues are not only responsible for image formation, but are also responsible for artifact formation and are responsible for some of the issues related to obtaining good quality images. Understanding these interactions allows us to use the ultrasound machine controls to optimize image generation. We will go through some of these ultrasound controls in the next part. Thank you for watching and hope you enjoyed it.